So hello everybody, welcome to the next 30 minutes of describing the datasets for this hackathon. So Sebastian will also come online afterwards, and myself, we will support you throughout the hackathon for the data analysis project. So step by step, going through them, starting with stroke rehabilitation related to motor imagery. So give you kind of a background. The data sets you have, they stem from the RecoverX stroke therapy. So this is a system we have which helps stroke patients, and nowadays also multiple sclerosis patients, to regain body functions actually, and it's based on motor imagery. So the patients, as you can see in the image here, they are sitting in front of a computer with an avatar, and they are told to imagine right hand or left hand movement. And the BCI is trained based on that imagination. And when it detects imagination, then functional electric stimulation is provided to not the hands, but those muscles here, such that the hand moves actually. So this is really a nice way of feeding back the sensory and actually the movement perception back to the patient. So this is kind of a nice closed loop BCI system. And as I said, we're going to provide you some data sets from these therapies, of course, anonymized and stuff, so everything is safe. Just to give you an idea how such a trial looks. One trial of left or right hand imagination lasts 8 seconds. So there is an attention sound in the beginning, such that the subject knows, okay, now something will happen. And then after 2 seconds, there is a left or right hand cue, an indication which hand movement to imagine. And then the patient has about 1.5 seconds to go into this imagination. And after 3.5 seconds, the functional electric stimulator, the FES, will provide feedback to the patient until second 8. And then there is a relax stimulus to the patient and the trial ends. So that's the 8 seconds. So we have provided data sets from 3 subjects, P1, P2, and P3, during 2 stages during the therapy. So as you can imagine, such a therapy is not only a 1 session, but it's really a couple of sessions throughout several months. So we have data sets from the beginning of the therapy, that's the pre-stage, and a data set from like after or one of the last sessions of the therapy, which is the post stage. And we have, again, for each patient and each stage, we have a training and a test data set. Training means, of course, this is when the classifier is trained, and the test is the data set when the BCI is providing feedback based on the training data. So this is the file names you get. Everything is inside. You can see a sampling rate, and the variable y is the data matrix, and the trig provides you the trig information, what happens at which point in time. So to give you an idea, or kind of inspire you to do some analysis, we also provide you some reference accuracies from 2 different pipelines. So one is the standard common spatial patterns plus LDA pipeline, and one is a novel pipeline we developed, which improves accuracy quite substantially. It's based on time variant LDA and principal component analysis. So there is a publication I will also share alongside the data, and you get an idea what not only methodologically the difference is. So here we get, for example, 77% for the standard classifier, but 92% for the improved classifier. But also we have different accuracies across not only subjects, but across different stages for the same subject. So that's really an interesting point, or an interesting aspect you could dive into. But of course, as for all datasets, you are free to do whatever you want, as long as it is kind of well explained in the end, and you get some exciting results. This is the montage. So we have 16 channels, and you see which channel index relates to which position on the cortex. There's an overview of the files, which is uploaded on GitHub, and we share the links in Discord when this presentation ends, such that you can get started. All right, now let's move over to the next data set. The next project is the P300 Speller project. And again, some background. So you might be familiar with the P300 wave, but in a nutshell, it appears when you are waiting for a certain stimulus, which occurs or which is embedded in many other stimulus you're not paying attention to. So one common or one very famous example is the speller, where you're focusing on a target character, on a character you want to spell, and all those characters, they flash in a random pattern. Actually, it's a row and column pattern. And when the character you're focusing at is flashing, then your brain will exhibit a nice P300 wave. And this P300 wave can be detected by the BCI and be used to detect which character you are focusing on. So that's a very famous example. Here you got 5 data sets from 5 different subjects recorded from the unicorn, I guess, with wet electrodes. So the electrodes are gelled, the signals are nice. And again, inside the data, which are MAT files, they contain the sampling rate in hertz, the data matrix, and also the trigger information. Good. So that's also I share a publication how you can use, for example, TVLDA for P300 spellers. Next project, steady state visual evoked potentials, SSVEP. This is also a very nice BCI paradigm. So the background is that when you are focusing on a certain item, a visual stimulus, which flashes periodically at a certain rate, then it's possible to detect this frequency of the stimulus you're focusing on in your brainwaves. So you would see, depending on whether you're focusing on maybe a 17 hertz or a 14 hertz stimulus, you would see this in the spectrum of electrodes recorded from the visual cortex. So one example would be avatar control. For example, you're moving through a computer game world with an avatar, and you have some flashing items on the corner of your screen. And when you're focusing on one of them, then the avatar moves into this direction. That would be one example. Here you got data sets, 2 data sets from 2 subjects with various frequencies. So we have 4 different frequencies, 9, 10, 12, and 15 hertz. They are provided as columns in the class info file. The data is recorded at 256 hertz. And the data sets have 11 channels. First is a sample time. Channels 2 to 9 is EEG, so you got 8 channels. Channel 10 is the trigger info. So this is an exact information whether the LED is on or off. And on channel 11, you get an output of the LDA classifier, which was used during the experiment. All right, there is also a publication you can use. You can read to make yourself familiar with SSVEP experiments if you're not familiar already. All right, next project is about unresponsive wakefulness and locked-in syndrome patients. So these are patients which are severely impaired. So they are, basically speaking, in a coma, and they cannot move their body parts. And they cannot react to the environment. So the question is, how much of their brain activity is left, and can they understand when you're talking to them? And to drive it even further with the BCI paradigm, is it possible to kind of communicate with them in a very rudimentary manner? So, for example, would it be possible to use a BCI to let them answer yes or no questions? So this is data sets you get here. This is a vibrotactile paradigm. So this is also something we call VT3 paradigm, because we have 3 different vibrotactile stimulation sites. There is one vibrotactor, so this is something that vibrates on the right wrist, and one vibrotactor is on the left wrist, and one is on the left ankle, right? So what happens is during the paradigm that all of them, they vibrate, not at the same time, but after each other in a random fashion. And the purpose of this arrangement is that when we ask a patient to a question, which can be answered by yes and no, then if the patient is instructed, or the patient can answer this question by counting or focusing on the stimulations on the right wrist, and for example, for a yes answer, and for a no answer, the patient can focus or pay attention on the left wrist. And the ankle stimulation happens like most of the time, and this is this stimulus the patient is not paying attention to. So this is also called distractor. And again, the whole signal and feature extraction pipeline is based on the P300. So again, when the patient, for example, wants to answer the question with yes, and it's counting the stimuli on the right wrist, and the stimulus appears, then the P300 wave is elicited in the brainwave, and it can be detected. So this has actually 3 or 2 levels, or at least 2 levels of interpretation. One thing is if the patient is able to understand and to answer the question at all. So if we don't, if you're not able to detect the P300 wave at all, then the patient might be sleeping. So sometimes you don't notice that, or the patient is too, let's say, impaired to understand the question or to answer the question. So this is kind of the first level to interpret this. The second level is if you really can discriminate, if you have the P300 wave and you can discriminate between right and left, then you can also identify if the patient answers this question with yes and no, which is a really groundbreaking communication path. And of course, you validate this somehow by answering questions where you know the answer already, to make sure that the BCI is not reporting any random result. The montage is a little bit reduced compared to the recoverix. So we have 8 channels here. They're more central, but also channel 2 and 4 cover the motor cortices. And subjects of the datasets you get from 2 subjects, P1 and P2. And what is very interesting and could be a starting point for your investigations or your hacking project is that the same patient, or actually both patients, reported very, very low accuracies, communication accuracies at 2 points in time. So we had several sessions with them, and they reported very high accuracies at another point in time. So the question is, one of the questions you could dig into is what the reason for that is. So you might be able to detect or to find any biomarker which explains this. Maybe the patient is just sleeping or something else. So in the data set, which are 8 files, you have the sampling rate, you have the EEG data as a data matrix, and you also have the trigger data. So what happens at which point in time. So here -1 is the distractor, +1 is the non-target, and +2 is the target stimulus. All right. Nice animation. Yes, so here is how the trigger channel, for example, looks throughout the recording. Cool. So now let's come over to the last 2. I think 2 are left, 2 analysis projects. They are invasive ones, so you get data which was recorded from ECoG electrodes, which are implanted directly on the cortex. The first one is the hand pose hacking project. So here you can see an image of the patient in the hospital who is participating in this experiment. So this was a young lady who was severely suffering from epilepsy, and she was treated in Japan by Dr. Kamada, and she got a surgery to get rid of her epileptogenic focus. And this was a two-stage procedure where she had electrodes implanted in the first implantation surgery, and then she stayed 2 weeks in the hospital, where lots of examinations took place to plan the eventual surgery, so the final resective surgery, where the parts of the brain were removed. And during these 2 weeks, we also were able to record some BCI experiments with her. So you can see that she was sitting in the bed. She was looking at the visual cue presented on the screen. She also wore a data glove, which captured her hand movement. So everything was recorded. And in the background, you can see a very tidy but well-sorted recording setup where all the channels were connected to an electrode headbox and recorded by the G.high amp. So this was kind of the environment we recorded the experiment in. And the experiment itself was about hand gestures, so high-level hand gestures, inspired by the famous hand game rock, paper, scissors, or you could also call it fist, piece, and open. So fist, piece, and open hand. And importantly, open is not like some relaxed state, but really open, stretch, because there is also the resting state, which was kind of putting the hand to a relaxed state. So this experiment was cued by visual stimuli, where we had a series of relax and task stimuli. So the relax stimulus just showed a scrambled picture. You can see here. This relax period was randomized between 2 and 3 seconds. And then afterwards, there was a stylistic gesture shown on the screen, which indicated which hand pose the lady had to form. So this was 2 seconds. And overall, we had 30 repetitions for each pose. So that means 3 times, because we had 3 poses, 3 times 30 repetitions, and all of them were randomized. What you get here is the dataset from this experiment. It was recorded at 1.2 kilohertz. The reason is that it was recorded with ECoG, so invasive signals. And the benefit of such an invasive recording is that you can observe frequencies much higher than regular EEG. So EEG is usually band limited to maybe 50 hertz, 40 hertz for standard analysis. And for ECoG, you can go even up to the kilohertz range. And what's very interesting when you process invasive data sets is that in the range above 50 hertz, there is the gamma and even high gamma range. And this is a very, very robust and reliable biomarker, which is for behavioral or cognitive tasks. So when you move your hand and you capture signals from the motor cortex, you can be sure that you will see very strong high gamma there. And high gamma activity, which is this biomarker, is the power change of those frequencies. So for example, when you take 60 to 150 hertz and you're band passing the signal in this range, and then you're computing the power, then you will see a very strong power change when the subject is doing something. So you will definitely see that if you're doing the processing correctly. Here is the location of those electrodes. So you get 60 electrodes, 60 channels from a high density ECoG grid, which was implanted on the sensory motor cortex. So it nicely covers sensory area and also motor area. The data is recorded raw and DC coupled, so there is no processing whatsoever being done to the data. And it was recorded from the right sensory motor cortex because the patient was moving the left hand. Well, actually, that's not true. It was moving the right hand, so it was recorded from left sensory motor cortex. Sorry for that. So it was contralateral. It captures the right hemisphere. Then in channel 62, because channel 1 is sampling time, channel 2 is 261 is ECoG, and channel 62 is the paradigm info. That tells you again what task was active at which point in time. So 0 was relaxed, 1 was fist movement, 2 is peace, and 3 is stretch or open hand. And additionally, you also get the recorded signals from the data glove in channels 63 to 67. So these are the 5 channels capturing thumb to little finger. All right. There is one MATLAB data file for you. There is a data description, a PDF, which essentially covers the slides I've been showing you. And there is also a publication from 2019 where we applied TVLDA to these ECoG hand pose datasets and showed how nicely we were able to classify the individual gestures. So I think we got over 99% classification accuracy for this subject. Good. Then I think this is the last one. It's again an invasive data set. It is captured during a very nice task during video watching. And here it's kind of a free run paradigm where the patient was watching a video, and the video shows a walk through the garden, which is actually the backyard of our company. And during this walk, several different categories, official stimuli are captured and shown. So you can see as an example, here there is a blank sheet of paper with a number written on it. And the background here is that it's possible with the right electrode locations capturing brain signals that you're able to discriminate the high level type of stimulus shown to the patient. So for example, if the patient looks at the face, you would be able to discriminate this based on the recorded signals from a patient looking at a digital number or something like this. So during this walk, basically 7 different categories were covered, or at least a subset of them. So there is, for example, as you can see here, the digits, so numbers. Since we recorded this experiment in Japan, we also get stimuli related to the Japanese language. So there are kanji, which is Japanese language, kanji symbols, and hiragana, which is also Asian language. There are also stimuli with line drawings, stimuli showing objects, and stimuli showing face and body parts. So that was an experiment also published, and you will get this publication, where the patient was really looking at visual stimuli, just showing those types of images in a controlled sequence. But this one is kind of an extension, an extension of this experiment, where the patient was watching this free walk through the garden. So of course you will also get the video the patient was watching alongside the data. So I've already talked a bit about this publication, which you also get. So it was published by by Christoph Kobella a couple of years ago. It's about real-time detection and discrimination of visual perception using electrocorticographic signals. So that's a bulky name of what I've just explained you. The background is that with a proper electrode location, essentially in the temporal base, like the bottom of the brain on the back, so to say it very frankly, when you have electrodes capturing brain activity there, then you will be able to discriminate the different types of visual high-level processing using data from these electrodes. Okay, then about the data sets you will get. So this is a data set recorded again at 1.2 kilohertz, where in channel 1 you have the time channel 2 to 161, so you get lots of ECoG channels. You have the ECoG signals. Then you have on channel 162, you have the digital input of the photodiode, which was recording the screen during the video playback. This was to synchronize the video with the actually recorded data. We can discuss this in the group if you have questions about that, but it's of course always important to synchronize the recorded signals from the brain to the real life events happening at this very moment to the patient. So that's where the photodiode feedback is used. Then we have stimulus code and the group ID from the task, which is from the stimulus, which is shown to the patient at this point in time. Data was not referenced, so you will see pretty a lot of line noise. So you will have to do some pre-processing before to get rid of that. Here you also can see the electrode locations. So this was basically the right hemisphere, and yeah, lots of motor cortex coverage, frontal lobe, temporal lobe, but also very important for these types of experiments here, temporal base fusiform gyrus coverage, where the most interesting signals will probably come from. You will get the publication I have shown you. You will get basically also the of course the data file, but also the information about what is shown to the patient. You will get the video file such that you know what's happening at which point in time, and also all other kind of meta information I was presenting to you right now. Great, so that's it from my side. I hope I was able to give you an kind of a basic introduction. Of course, you will have deeper questions in the Discord groups, but Sebastian and I will do my best to support you throughout your journey through this hackathon. So thanks for now, and see you on the other side.